So it's very obvious. The discrete returns are very easy to compute. What is the percentage change of our share price? Well, that is 120 divided by 100 minus 1. So that's plus 20%. And this is just really the number that people are talking about when they talk about returns. So if you don't hear any kind of additional word next to it, like we have here, then people always refer to the first definition. That's the standard return. And most of the time we're going to use this definition. There's some very few exceptions where we have to use the second definition. That's, for example, this formula by Black-Scholes and Merton, which I mentioned. They use the second definition. So for the sake of this class, you don't have to make a choice. I will always tell you which version to use. Right? So there shouldn't be any ambiguity around in problem sets or in the exam questions. You will always get to know from me that which version that you should use. But kind of the standard version would be the first one, and the second we only use when it makes sense for a model. Right? So having said that, because in the option pricing formula, the second definition is very often used, the book by Hull, for example, John Hull decided in his book to only use the second definition. Right? So if you look with that book, you will only find the second definition. So what is the second definition? Well, as you already see from the formula, it uses the natural logarithm of the fraction s capital T divided by s little t. So maybe let's do first a quick computation. So how does that work out in our example? So that's the natural logarithm of 120 divided by 100. And if you plug this into your calculator, you get roughly 80.23%. Right, so a different percentage number, which is not really intuitive. So first of all, how could we think about this? And I was, like in my attempt to visualize this, maybe think about distances. In Europe, continental Europe, we measure distances in kilometers. In Great Britain, they measure distances in miles and yards and whatever, right? And that's basically the same thing. Now you have just two units for the return. You have the standard unit, right, which we can easily interpret as plus 20%. And now we have a second way of measuring returns. It's still the same distance between two share prices, right? It's the distance between 120 and 100. But now we're just writing another number in a different unit to it, right? Or think about one in euros, the other one in US dollars, right? There is a fixed relationship between a value in euros and value in US dollars. That's kind of an exchange rate. I was trying to visualize this here using this ruler. So the top ruler shows you the discrete return, and the bottom ruler shows you the corresponding logarithmic return. So the 0 point is our starting point. So our starting point here was the share price of 100. That's where you basically put the ruler. And then you basically check where's the share price at the end of the period. So that was 120. And now you can just pick the two definitions. Well, the top ruler just says 20% return, and the bottom says, well, 18.23%. We measured the same thing, it's just two different units. It gets a little bit more complicated because we have different rules of computation for the discrete return and for the log return. And I'm going to show you these rules in a second. Okay, if you compare now these two rulers a little bit, one thing that you will find is, first of all, that the intervals that you have at the bottom are not equally spaced anymore. Right? So here, basically €1 corresponds to 1% in the discrete return. However, here the units are different. So, for example, here you have a difference 30 to 40%, so that's 10% difference. And here, the same distance basically spans more than 20%. Right? So the intervals become smaller in the negative scale. Right? So the logarithmic scale is not linear. That's very apparent for this. The second observation that you could make is that the logarithmic return, just in terms of value, is always below the discrete return. Right? So here we have 20%, and here we have 18%. 18 is smaller than 20. And the same holds true here. So here we would have minus 50%, while we have minus 70 for the log return. Minus 70 is smaller than minus 50. Right? So log returns are always smaller in magnitude. So far the definitions, and again, you don't have to make a choice. There will be some models like option pricing where we just have to use the log return. And the reason is because in the theory, to get to the solution, you require this to be able to solve it. But most of the time, we're working with the discrete return. Okay, so if there are no questions, then let's kind of study the computational rules. Now there are two things that we need to know. The first thing is compounding. That means suppose you have two returns for 2 years, first year, second year. How do you basically compound the two or connect the two to compute a return for the full 2-year period? And the second is, if you have a multi-year return, how do you annualize that? Annualize means, like, typically we express returns per year, but what happens if you have measured the return over 5 years? So what is the average per year over the 5 years? Right? So compounding and averaging is that what we have to think about. And that works differently for the two. And by the way, of course, computing logarithms requires your calculator. It's a bit messy because the numbers are not around here anymore. Right? However, the computational rules that we study now on the next 2 slides are much simpler for the log return. So there are some benefits of doing this. So, again, let's do a short example here. I think the numbers are already on the slide. So we're going to look at a 2-year period. And we have 2 returns given here. So in the first year, we have a return of plus 10%, and the second year we have a return of minus 10%. So we have R1 equals to plus 10%, and R2 equals to minus 10%. The question is, what is the return over the full 2 years? So how can I compute the 2-year return out of the 2 single 1-year returns? Yeah, and there's already a small hint here on the slides of how you could do that. So for the discrete returns or standard returns, you have to use the so-called multiplicative compounding rule. So let me show you the formula first. So what you have to do is, first of all, you have to add 1 to the return, and then you have to create the product out of this. So the 2-year return is going to be 1 plus the first year return multiplied with 1 plus the second return minus 1. That's what we call multiplicative compounding. 1 plus the return multiplied with 1 plus the return. So if we plug in the numbers here, we have 1 plus 10% multiplied with 1 minus 10% minus 1, and you get roughly minus 1% from this. Exactly 1%. Right, suppose you start with a share price of 100. What's the share price after 1 year? Well, in the first year, you increase the share price by 10%. So you start with 100, you end up with 110. Right? Now, in the second year, you lose 10%, but the 10% now has to be based on the 110 share price at the beginning of the year. So 10% of 110 is 11, right? So your share price goes down by 11 euros. So 110 minus 11 gives you 99, right? And if you compute the return based on 99 divided by your initial share price of 100, you're at minus 1%. More formally, if you want to kind of see that this is the correct rule, because we are now in the master program here, I sometimes do these little proofs to just illustrate to you that these results hold more generally. Let's maybe formally do this by plugging in the definitions from the previous page for the first year and the second year return.